Star A and star B are separated by a fixed distance of 4.8 light years as measured in a reference frame in which they are stationary. An observer P at rest in a space station moves to the right with speed 0.78 c relative to the stars. A shuttle S travels from star A to star B at a speed of 0.3 c relative to the stars. State the value of the maximum distance between the stars that can be measured in any reference frame. The maximum possible distance is a proper length, and the proper length is measured in the reference frame in which this distance is stationary, and it is given that 4.8 light years it's a distance measured in a reference frame where stars are stationary. And actually let's denote a reference frame in which stars are stationary. I would like to denote it as S, but to avoid confusion, since shuttle is also S, let it be just Y and X, and let moving reference frame be just primed X primed Y primed, and this distance is 4.8 light years in reference frame where stars are stationary, and hence it's a proper length, and the proper length it's a least possible distance. And for example, the observer P will measure contracted, it means less distance than and it will be a value which is less than 4.8. So the answer for A is just 4.8 light years. B. Write down the speed of a shuttle relative to the observer P using Galilean relativity. Galilean its usual transformation of velocities, and you may deduce without any calculations since they are moving in the same direction, and it seems that for observer P, shuttle S is moving to the left because P is moving faster, but with a speed which is just different. So speed of a shuttle relative to P using Galilean relativity is just negative 0.48 c, because 0.78 minus 0.3 it's just 0.48 c, or you may use formula directly. It is given in a data booklet, and for the Galilean relativity you primed it means in moving reference frame, and it means what, relative to the observer P or relative to the space station, and it is equal to u minus v. And what is u? U is speed in not primed reference frame relative to stars, and you can see it's plus, and plus means to the right, minus to the left, so it becomes just plus 0.3 c, and v it's the speed of this moving reference frame relative to the stationary reference frame. So here it's 0.78 c, and also it's the speed of the observer P, so it's minus 0.78 c, and you can see that it's the same, negative 0.48 c. Minus means that it's to the left. The next question: calculate the distance between stars A and B relative to the observer P. So since distance is 4.8 in a reference frame relative to the stars, and it's a proper length, all other observers in any other reference frame which is moving relative to the stars will measure what contracted length, and the observer P also will measure the contracted length, and it can be calculated as 4.8 light years divided by gamma, where gamma factor for the speed of 0.78 is equal to what? It's 1 over root 1 minus 0.78 c and squared over c squared, and it is equal to and you can see that it's approximately 1.6, hence this distance becomes 4.8 light years divided by 1.6, and it's what, just 3 light years. The next shows that the speed of shuttle S relative to observer P is approximately 0.6. So it means we should use what? A formula of special relativity. What formula actually is the same? U prime is not actually the same, a bit different. What is the difference? That denominator rises, which is 1 minus u v over c squared. This formula is given in a data booklet, and hence its speed or relative speed of a shuttle S in relative to the observer P, because P is a moving reference frame, so it's primed. U is speed in not moving reference frame or reference frame relative to the stars, and it's what? It's 0.3 c, and minus v, it's again speed of moving reference frame or observer P relative to the stars, and it's 0.78 c. Notice that operation is minus, but it is moving to the right, so it's plus. In general it may be also negative, and it's also in general maybe negative. Notice that it's the same as for the Galilean, but for special relativity the denominator rises and it becomes 1 minus 0.3 times 0.78 over and c and divided by c squared. Let it be c squared and c squared, and it becomes minus 0.63 c. Minus indicates that it's to the left. Speed or velocity of a shuttle is to the left relative to P. The next, calculate the time according to observer P that the shuttle S makes to travel from star A to star B. And there are 3 ways how to calculate this time, and let's consider all these 3 methods. The first method is to use a formula. It is given in a data booklet. Delta t primed is equal to gamma delta t minus v delta x c squared. And it is equal to, what is gamma? Gamma also can be calculated as what? 1 minus root 1 minus v over c squared, but gamma, it's for v is 0.78 because not primed, it's there is a reference frame relative to stars, where stars are stationary, and we consider a primed reference frame to be this moving space station and also moving observer with speed 0.78. So here we should consider V to be 0.78, and it will be the same factor 1.6. So it becomes 1.6 delta t. What is delta t? It's time required to travel in not primed reference frame or in reference frame relative to stars, and time it's what? Distance divided by speed, and in this reference frame you can see that what distance is 4.8 and what speed is 0.3, so time is distance 4.8 light years divided by velocity or speed 0.3 c, and what is light year? It's speed of light multiplied by years, so c cancels and we get answer to be in years. Minus v is 0.78, it's speed of moving reference frame relative to the stars. Delta x is distance in this reference frame relative to stars. It's what 4.8 light years, 4.8 light years, and the c here, and over c squared. And again you can see light years, it's c and years, c and c squared cancels, and hence we get that it is equal to 19.6 years. 19.6 years. The second method. Let's write here. 4.8 light years divided by 0.3 c, it is equal to what? It can be easily divided. It's 16 years. It's time required a shuttle to travel this distance in reference frame relative to stars A and B. But if we consider a shuttle will measure a proper time, because two events occur at the same place at the shuttle. If we consider new reference frame relative to a shuttle and reference frame relative to the stars, we'll measure dilated time, and relative to the shuttle we'll measure proper time, and proper time can be found as 16 years divided by gamma, and gamma for 0.3 and gamma for 0.3 you can see it's 1.048, so divided by 1.048, it's for v is 0.3 c, and it's a proper time, it's time relative to s, to the shuttle, and it's proper time. And now let's consider the observer P, and relative to P, stars, or actually not stars, shuttle is measured to the left with speed 0.63 c. And P will measure what? Dilated time. because proper is in shuttle. And so the first step, we consider reference frames, two reference frames, one shuttle, another is stars. But here we consider shuttle and observer P, or space station. And this situation looks like this, that shuttle is moving to the left with speed 0.3 c, and proper time, it's the time for something measured in a shuttle, is this value. It's a proper time. And P will measure dilated time, and dilated time we should multiply by gamma, but gamma calculated for 0.63, and it's 1.288. Gamma is 1.288, for V is 0.63 c, and hence required time becomes 16 divided by 1.048, it's proper time, and multiplied by 1.288, and it is equal to here P is like stationary stationary reference frame, and this particle or this shuttle S is like moving reference frame, and two events occur at the same time in the moving in S. It's absolutely the same as laboratory and a muon moving, something like that. I hope it's clear, and you can see that it becomes 19.6. There is a bit difference due to rounding, but in general it's something in between 19 and 20 years. And years again, years. And the third method. Observer P is moving to the right with speed 0.78 c, and relative to the observer P, stars A and B, this not primed reference frame, is moving to the left with speed also 0.78 c, but to the left. So it seems that for P, it seems that stars, this like reference frame, is moving to the left with 0.78 c, and for P, speed of a shuttle is also to the left with speed 0.63, or it's negative 0.63 c, and for P, the resultant speed of a shuttle is what? Difference. Why? Because for P it seems that this, let's call it a rocket is moved in this direction, but no, it's actually this AB is moving faster, so shuttle is moving actually to the right with speed 0.15, which is difference. And what is time? Time is distance divided by speed, but distance relative to AB is 4.8 light years. But for P, this distance becomes what? It will be contracted, so we should use what these three, where is it, this. So we should use contracted length. Why? Because relative to p, stars is moving with speed 0.78 c, and p will measure contracted length. So we should use 4.8 divided by gamma for v 0.78 c, or 3 light years, and delta t primed. Oh, it doesn't matter, delta t, to indicate that p is generally moving to be like this, to be moving reference frame. So let it be delta t primed. So, and finally you can check that it becomes the same. 3 divided by 0.15, and again light years, c times year, c cancels, and it's 20. And again, difference is due to roundings, 20 years. And let's denote delta t primed finally here. And the last question, identify and explain the reference frame in which the proper time for shuttle S to journey from star A to star B can be measured. Shuttle measures proper time as the events occur at the same place. And that's all for this question.